Welcome to the 21st section of the course OS Persistent with C++ and Qt. My name is Carlos, and now we're going to have a quick example of the forward chaining algorithm. The aim of this video is to let you know how the inference engine works by the forward chaining algorithm, which is the principal algorithm to make OS Persistent think. So let's define a small set of rules. There are just 5 of them, and give them to A and E the value of 1. Before continue, please remember what's the goal of the inference engine. Of course, the goal is to reach conclusions. But what are conclusions? We haven't defined the concept of conclusion. Conclusions are atoms that are in the consequence, but they shouldn't be in the antecedents groups. From the rule list, now we can know which ones are conclusions, right? To know that, let's split the antecedents and the consequence into 2 groups. So the antecedents are A, B, C, A, I, P, F, A, P, N, A, P, and B. Now you might notice that there are some duplicate atoms, and we shouldn't have duplicate atoms. So let's process to eliminate them. A, B, C, E, F, and M. B, F, and M. Now, in our code, this group will be a container, and I would like you to give you some homework by the next question. Which STL container will be the adequate to represent this group? That's your homework. So, okay, let's identify the consequence from our rules. Those are D, G, and C. Typically, the values of the conclusions are unknown, and we need to identify those values to give a solution to the customer. Inferring conclusion is the objective of OS Persistent, remember. So let's demonstrate what is the basic procedure of the forward chaining. In any case, if we measure the environment of the user gives us the value of A and E, we can infer the conclusions in the following way, by draft. First draft. Let's first write down the values of A and E. By those values, we will know that we need to use the modus ponens. A value is 1, B is unknown, C is unknown, D is unknown, G is unknown. So we can infer anything here. We need all the antecedents to have a value of 1. For example, in this rule, E is value 1 and A is value 1. So the whole is a 1 because it's an operand. So we can infer that the value of M is 1 by modus ponens, of course, and P value is 1. So let's continue. P, we know that it has a value of 1, but F is unknown. B is still unknown, C the same, C the same. A is 1, P is 1, M is 1, and we can infer in this rule that the value of B is 1 and the value of F is 1. So the last rule, 1, 1, and 1, we can also infer the value of C is 1 and D is 1. So we finish the first draft. So you might notice that we already have the value of D, which is a conclusion. Therefore, if the user just wants the value of D, then we can finish the inference. Well, what if the user wants to know the value of G or C that are still undefined? We haven't determined these values, so we need to pass through the rules again in the second draft. Just copy again the rules. One, and C has value of 1. We might put those values here just to see them. We can infer so that value of D is 1, as I already know, but G is a new value and has 1. E and A still the same. M and P has value already, so we don't have to put it again. P and F have value, so we can infer that B, C, and C have some value. I think that. Oh. So the only one left that we didn't know the value was C. Okay. This is 1, this is 1. We already have a value, C as well, but C was the last one, the missing. And it has the new value 1. A is 1, P is 1, M is 1. Well, we already have the values of B and F, so we don't have to process it again. And this rule was also implemented, so no care to do it again. Finally, we already have all the needed conclusions. So we can infer the results in the user interface. So to conclude, this is the simplest way to show the forward chaining procedure or algorithm. And you might notice that we will need containers to hold the antecedents, the consequence, and the conclusions. Moreover, we might need to link the atoms ID with their values and make some optimizations. One interesting optimization, by the way, is to skip irrelevant rules. A rule whose atoms are set already is called irrelevant rule. This is because rule values can change and we don't need to examine them again. So this was the last opinion, and this is the end of this video. In the next one we will need to start our implementation of the inference kernel. So please share, comment this video, and have a look to our website geartext.com.mx. Thanks.